Hello and welcome to Innovative in Education's Organic Chemistry series. My name is Mike Evans and I'll be your guide through the wonderful world of organic chemistry this semester. And today we're going to be talking about nucleophuse dissociation, which is the second elementary step, the third elementary step that we're going to be looking at. The first two we've looked at proton transfer and the SN2 or bimolecular substitution steps. And today I'm going to review a little bit of what we talked about with SN2 and go into more detail on the third elementary step, nucleophuse dissociation, which is very important for elimination reactions, which we'll explore in more detail, as well as the SN1 process, which is a substitution that can form carbon heteroatom bonds through the intermediacy of cations, which is a little bit different from SN2. And it takes place over multiple steps, so it's interesting in that respect. Now, just to review a little bit about what we talked about with the SN2 reaction, remember that it's displacement of a leaving group for a nucleophile, or by a nucleophile. So a nucleophile will come in and attack an electrophilic carbon, as you see in the diagram above my head here, and a group called a leaving group will take a pair of electrons along with it and leave as an anion. So on the side of this diagram, you can see that the carbon-carbon bond has been formed by the attack of a nucleophilic or electron-donating carbon on an electrophilic carbon, and a leaving group has taken a pair of electrons and left with those electrons. We give that leaving group a special name. It's called a nucleophuse, and so we're going to talk about, in particular, this second arrow of the process up here. The second arrow where the leaving group is taking the electrons with it as it goes away. Now, we talked about how nucleophilicity and leaving group ability depend on pKa. Nucleophiles act like bases. They donate electrons. As a result, stronger bases will also be better nucleophiles generally. We also talked about how leaving groups are often good acids. These are groups that are very electrophilic, that want to accept electrons and take them with them, take them away. As a result, compounds that are very strong acids, the conjugate bases of those compounds, will be good leaving groups. They'll tend to be very stable anions like Br-, Cl-, the tosylate anion if you've dealt with sulfonate groups yet, and things like that. Very stable anions. Now, one point I did want to address is this issue of stereochemistry and steric interactions in the SN2 reaction. So we didn't talk about this in too much detail last time, but steric interactions are very important in thinking about the SN2 reaction. So not all compounds with good leaving groups can undergo SN2. This is very important to keep in mind. So the SN2 reaction, for instance, cannot occur for compounds that possess quaternary centers, compounds with the leaving group on a quaternary center, which just means a center with 3 carbons attached to it. So this carbon in the center here is a quaternary carbon, and it can't undergo SN2 because for it to undergo SN2, it would have to be attacked by a nucleophile with this very sterically hindered position. We don't see that occur. So keep that in mind. Quaternary carbons do not undergo the SN2 reaction. Luckily, they do undergo a kind of substitution that we'll look at in detail today called the SN1 reaction. Last thing I'll say about SN2 is that remember that the stereochemistry of the reaction is dictated by orbital considerations. So last time we identified the SN2 reaction as an N to sigma star kind of orbital overlap in a sigma-type fashion. And this means that the nucleophile, if the nucleophile is my pen, it approaches the electrophile from the back. So if the carbon leaving group bond is oriented like this, the nucleophile approaches from the back, and this leads to an inversion of stereochemistry in the final product. So keep that in mind as well. Now today we're going to look in detail at the nucleophuse dissociation step. And nucleophuse dissociation is this sort of half SN2 reaction that you see right here. It's interesting because it is sort of this half SN2, but this intermediate, this cationic intermediate that you see here, can undergo a lot of other kinds of reactions. So nucleofuse dissociation opens up a lot of interesting mechanistic possibilities for us. And a lot of different species can undergo this reaction. So, very first thing, I just wanted to take a look at the general scheme here. What you can see is that a leaving group, in this case Br, is taking electrons with it, just as we saw in the SN2 reaction, but it leaves behind this cationic intermediate and Br minus. Now, Br minus is a fairly stable anion, and this is sort of a general pattern for nucleofuse dissociations. The anion that undergoes the reaction doesn't tend to be too reactive. What we see reactivity out of are the cations. The cations are really the things that are going to go on and react further. The anions tend to just sit around and not really do anything. And as a result, we see a lot of this step under acidic conditions, conditions which favorably stabilize positive charges. This stabilization means that the cations are around long enough to do further chemistry. Now, this is an example of an interesting kind of orbital interaction here, because there's no bond making at all in this step. It's completely bond breaking. As a result, it's not really a sigma or pi type interaction as we talk about. It's actually a sort of no bond interaction. It's completely bond breaking. As a result, we call this a sigma to A, and I put A in quotation marks here because it's a very promiscuous A, no bond interaction. So we won't have much to say about the orbital interaction here, to tell you the truth. So to move forward, cations very often undergo this kind of chemistry. Dissociation can often generate a more stable cation or a more reactive or say productive cation on the basis of this nucleofuse dissociation step. So what you're seeing here is this protonated ether is undergoing a nucleofuse dissociation in which the oxygen takes the electrons with it. So that very electronegative oxygen pulls electrons towards itself, leaving behind a carbocation, here on my left, and a neutral molecule of methanol. You'll see this very often, and again, it's most often these carbocations that will undergo further chemistry. Anions can also undergo this chemistry, and because the nucleofuse takes electrons with it, it actually leads to a neutral product in which carbon is in this very unique 2 oxidation state. So we usually see 4 bonds to carbon, either 3 or 4. Here's carbon in the oxidation state of 2, so it's neutral with 2 bonds to it, attached to it. And this is an interesting intermediate that you may have seen called a carbene. And again, the carbene is going to be the thing that's going to go on and do further chemistry in this case.